Hi, my name is Rich, and I'm a Freescale developer in my spare time. If you're anything like me, you probably got really excited the first time you heard about a computer on a chip. I mean, what a great idea. An entire computer all on one chip, right? Maybe you got on the phone back then and, ordered it from James Electronics or DigiKey or somebody like that. Showed up in the mail a few days later. I mean, this is great. You're super excited. You know what this thing looks like even before you get the box opened, right? I mean, it's got 40 pins, it's got dual inline package, glass EEPROM window. So maybe once you got it open, you were a little bit surprised. I mean, where's that DB25 connector I was expecting to be on the back of this thing? I mean, this is a computer on a chip, right? I got to be able to log in, I got to be able to program it, I got to be able to do all sorts of things, right? It's interactive, right? It's a computer. Anyway, you got into it a little bit more, and you learned that it wasn't really that kind of a computer on a chip. This is more of a programmable chip than a computer on a chip, right? You had a software development environment over here running on your real computer, right, where you could write the program and compile the program, and then you could download it to the programmable chip. You could maybe see what works, what doesn't work. Then you could go change the program over here and try it again and things like that. And eventually you'd get your program to run. But when you were done, you really just had kind of a smart programmable chip. It wasn't really a computer on a chip. It wasn't quite what you were expecting. There was another problem with this too, right? I mean, you bought this computer on a chip because it had all these fancy peripherals, right? It had analog to digital converters, pulse width modulators, it had, timers, flash memory, or EEPROM back then, or something like that, right? UARTs, all sorts of great peripherals that you wanted to take advantage of and you wanted to connect to your embedded system. Anyway, when you get over here to your software development environment, then you get this 500-page reference manual that basically tells you, how to talk to I/O registers and all sorts of, really intimate details that maybe you weren't quite that happy to learn about, right? Basically, you found that, in order to write a byte of flash memory, you had to go through all these algorithms, you had to read all sorts of things, and, it was a lot of work. And all you wanted to do was use the flash memory, right? All you wanted to do was take these really cool peripherals, and you wanted to just kind of connect them together at a high level, right? You wanted to take something from the analog to digital converter and, do something with an I/O pin and things like that. But you didn't want to have to learn how to use, or how to talk to or program an analog to digital converter. You just wanted to use it. Anyway, one of my goals in life is to bring embedded systems development to the masses, right? I think there's a lot of people out there who aren't using embedded systems, these really hot, cool microcontrollers who could be using them, right? These are, people in education or researchers doing low-volume work, they want to connect up stuff in their lab or whatever, or home hobbyists, right? I mean, I want to scatter these things all throughout my house, throughout my yard, throughout everywhere, and make them all talk to each other and do cool things for me, right? But I don't necessarily, well, actually I do, but not everybody necessarily wants to get intimate with their MCU in order to do that, right? They'd like to just be able to pick out an MCU that has all the features they want, connect up the things together at a high level, and then be done with it, and have a really great, cool thing that they can show people, or things that'll do useful work in their lab or wherever. Anyway, let's see how the badge board might be able to help us do that. Okay, so here's my badge board. We're going to play a little game. It's not a very exciting game. It's Pong or paddleball or whatever you want to call it. It's a little different. It uses the accelerometer to move the paddle and has sound effects. Let's see how I do under pressure. Okay, you can see we move the paddle, right? Anyway, there we go. I bounced it once, I bounced it again, I bounced it again. Oh, this is a lot better than I usually do. Anyway, so there we go. I lost. Anyway, what's exciting here isn't that I can play Pong or paddleball on the badge board. Okay, what's exciting is how I got here. Okay, what I didn't do is start with my development environment over here and my 500-page reference manual, read a big, read up on analog to digital converters and timers and things like that, and write a program and then download it to the badge board and have it not work, and then go over here, edit it, and download it again, and eventually get it to work. I didn't do that. Okay, what I did for this program is I started with a dumb terminal. A terminal emulator running on my PC, okay? And I hooked it up to the USB port on the badge board, and I talked right to the computer on a chip. Okay, the computer on a chip is running an entire operating system. Okay, he exposes a virtual COM port out of the USB, and he's got an editor, a transparent line-by-line compiler. As you enter your program, it's automatically compiled. An interactive debugger, a flash file system where you can store multiple programs, all running right here on the computer on a chip. Okay. This is what I dreamed of. This is the DB25 connector sitting on the back of the chip. And if this chip has USB, like a 51JM128 or a 52221, you can connect via USB. If it has Ethernet, like a 52233, you can connect via Ethernet. If it has a Zigbee wireless transceiver sitting next to it, like a 1320X, you can connect to it via Zigbee wireless. You don't need any wires, no USB or Ethernet. And you can log in write your program, edit your program, debug your program, get your program running, save it, and then you can even make it auto-run when you turn the power switch on. Okay, we're running a basic program here to play Pong, okay, paddleball, whatever. It's 93 lines of code, okay, and that includes comments, okay, probably more comments than I should have put in it. Anyway, so 93 lines of BASIC, and we're playing Pong, okay? In BASIC, the operating system understands all the peripherals built into the chip. He understands analog to digital converters, he understands pulse width modulation, he understands digital I/O pins, everything, okay? It's one line of code in BASIC to read an analog to digital converter. Basically, you can bind a variable, like tilt is the variable I use, to an analog to digital converter on a pin, and then from then on, when you read that variable, instantaneously in real time, you've got the number of millivolts on that pin. You can just refer to it in the basic program. Likewise, when we're generating audio signals, I can just bind another variable, maybe one called audio, to a frequency output pin that's connected to this buzzer, and I can say let audio equal 1,000, and boom, I've got a 1,000 hertz signal here using a pulse width or a timer module. Basically, in BASIC, everything becomes easy. You don't have to read the 500-page reference manual. You don't have to, understand I/O registers or anything like that. You can do timers, you can do interrupts, you can do all sorts of things. You can have watch points, break points, all sorts of things in BASIC. One line per operation, as opposed to, the 500-page reference manual. Then in BASIC, basically, you can connect together all these fancy peripherals that you got that you wanted with high-level statements. You can take an analog input from one and you can decide to do something on a digital output pin as a result. Basically, you tie together all your complicated peripherals using simple statements in BASIC, and the operating system knows how to manage them. And the operating system knows how to manage them for the different chips. And it's the same regardless of which chip you're on. Anyway, we'll be right back. Okay, one more thing before we get into the actual demo. We're going to go into the code. There's another thing that's missing here. Okay, remember how I talked about the Zigbee wireless? Freescale has this card, the 1320XRFC, that's really, really cool, and it will plug into the badge board. You got to solder a connector on it, and actually there's a little fly in the ointment here. You got to lift one pin of the MPR-084 off its pad because the IRQ pin isn't open drain like it should be. And so basically, in order for this guy to be able to drive the IRQ pin, you need to basically remove his IRQ pin. Otherwise, they kind of fight when this guy's not asserting an interrupt and this guy wants to assert an interrupt. He doesn't actually win most of the time. Anyway, so other than that, a little trick with a soldering iron, you can now plug the wireless card into the badge board, and now the badge board has wireless. Right? Basic programs, not only can you remote control them, log in and write your program and debug your program over wireless, basic programs can talk to each other over wireless. So for example, a basic program running on this badge board can actually talk to a basic program running on another badge board, and he can modify variables on the other board. And if those variables happen to be bound to pins, like for example the buzzer, he can make the buzzer run over there. Or you could have, this guy hooked up to a light switch and the other guy hooked up to a light, and you can make the light switch work. And we'll show a real simple example where we can actually use the accelerometer on this badge board to control the intensity of an LED on a different badge board, using analog input on this one, analog output on the other one, and Zigbee to tie them together. Anyway, and like 10 lines of basic program on total between all of them. Anyway, let's go take a look at the anatomy of the basic program. We'll be right back. Okay, so here's the badge board. I turn it on, and you see we're running our basic program, and I'm going to hook it up to the terminal emulator, and the program's going to keep running. And what we're going to do is we're going to break in by pressing Control-C, and we're going to stop the program. And basically, we're going to enter an interactive debugging session. Right? So, I stop the program. I press Control-C. It says stop at line 850. You'll notice that we stopped in the middle of an audio sequence, and so one of the output pins of the MCU was generating, whatever that was, a 500 hertz tone or whatever it was. And so we have a variable, a basic pin variable that's bound to the output pin. So what I did is I just set it to 0 to turn off the tone so we could talk.